Here we go. We're finally going to start talking about air columns. We've done a little refresher to remind you about the connection between frequency and wavelength. Low frequency means low note, which means a long wavelength. High frequency means high frequency, which means a short wavelength. And then this idea that speed of sound depends on temperature. So if we need to figure out the speed of sound, we would need to know the temperature. Okay, if you're into music or play musical instruments, especially wind instruments, this is going to be hopefully right up your alley and maybe a little bit kind of common sense. In physics, we're going to divide air columns into two general kinds of air columns. There are air columns that are open at both ends, and then there's air columns that are open at one end and closed at the other end. So I typed this, what did I say here? Yeah, recorder. So in elementary school, a lot of people have to play the recorder. The little picture I stole offline, the end that you put in your mouth is like way up here, and this little thing down here is actually an opening. So a recorder has an opening just in front of where you put your lips, so it's open kind of close to your face, and then this end is also open. So a recorder is going to be an instrument that we say is open at both ends. If you play the flute, you hold it sideways to your face and you blow over this little hole. That hole is an opening. It's got an open end kind of by your face and then an open end farther from your face. So think back to the good old days when you played recorder. To play recorder, to change notes, you had to cover the holes. Let's say you cover a whole bunch of the holes, all 5 of them. Then really what happens is you've got an opening here by your face, and then this hole, 1, 2, 3, 4, 5, let's say this hole is the next hole that isn't covered. Then the air column from here to here, that's the air column that's vibrating. I'm going down to this hole because I said you didn't cover it, so that's where the next opening is. That's a long distance, so longer wavelengths will fit in there. Longer wavelengths go with low frequencies, so we'd hear a low note. So think back to your recorder days. If you covered up a whole bunch of holes, that played a low note. As opposed to, let's say you only covered 3 holes. So one hole, 2 hole, 3 hole, then this is the next open hole. If that's the next open hole, then the length of the air column goes from the opening by your face to that open hole. That is a shorter air column. Literally, it's less centimeters from the opening by your mouth to that next open hole when we only cover fewer holes than it was over here when we covered more holes. So it's literally a shorter distance. A shorter air column means we're going to get shorter wavelengths. If the wavelength goes down, that means the frequency goes up. So shorter wavelengths mean higher frequency, means a higher note. So from your intuition, if you played recorder, when you covered a whole bunch of holes, basically what you were doing is you were making the air column really long, and a really long air column means a long wavelength. Long wavelength means a short or lower frequency, which means a lower note. And then the flip-flop, anytime you have a short instrument, the short instrument means shorter air columns, means shorter wavelengths, means higher frequency. It's the similar logic with other instruments like a clarinet. If you played the clarinet, it's got that wood reed, and you literally put that part in your mouth, closing it off. So there's a closed end in your mouth, but the other end of the instrument is open. Brass instruments like trumpets, trombones, tubas, you kind of close the end when you put your lips in that mouthpiece thing. So it's closed by your mouth and open at the other end. The physics is the same, whether it's a clarinet or a trombone or whatever. Well, trombone doesn't have holes, so trumpet. But basically, when you play the instrument, you're changing the length of the air column. If you change the length to make it longer, you're going to be playing a lower note. Long wavelength, low frequency, low note. And if you play it, if you make the instrument shorter somehow, shorter means shorter wavelength, means higher frequency, means higher note. Okay, here we go. there's one rule for standing waves in air. There's one rule for these vibrating air columns, but it's a dumb rule because the rule pictures the sound waves as transverse waves. I don't know, if I was around, maybe I could invent a better way, but too late now. This is the path that everybody follows. We know that sound is a longitudinal wave. If I was going to draw a sound wave, it would be like I did in that earlier video. I draw some bunched up air, then some spread out air, then some bunched up air, then some spread out air, over and over again. If I was going to label a wavelength, I'd say a wavelength is from like the bunched up to the next bunched up. But when people do these standing waves in air, they go back to regular standing waves and they picture and pretend that the sound waves are transverse. So instead of drawing regular sound waves, we're going to draw sound waves like we did in the last topic. We're going to draw them as standing transverse waves. So maybe something like that, reflected and interfering with itself. So there's the twin. And that's how we're going to draw standing waves in air, even though air would make a longitudinal wave. So for our vibrating air columns, we're going to draw them this way, even though sound waves really look like that. Little things when I draw them this way. So what I drew in red, a full wavelength would go from here to here. When we did vibrating strings, I sometimes talked about the football shape. The football shape goes there to there. That's half a wavelength. What we're going to use today is we're going to do a shift, and we're going to kind of look at from here to here. If I drew that much of a standing wave, we're starting at a crest, we're swooping down to a trough. The reflection is trough to crest. That much of a wavelength that I just doodled out is also half a wavelength. So we're going to see that shape over and over again. Kind of a sideways hourglass is half a wavelength. Okay, so right off the top, we know that sound is longitudinal and not transverse, but we're going to draw our vibrating air columns as transverse just to help us picture it better. There's one rule. The rule is that when we've got a vibrating air column, they're going to form a standing wave such that there is a node at the closed end and an antinode at the open end. Oops. So here's our important rule for vibrating air columns. This is going to be another one of those things that's going to be a little bit maybe confusing as we go through it, but at the end, I think it'll all click. So bear with me while I talk you through this funny chart, and then the examples will make it click. So we're going to follow our rule. We have to have an antinode at the open end and a node at the closed end. Remember, node is the dead spot. So a node would be, kind of messing up my diagram, a node would be there. And the antinode is kind of this part, the lively part. Okay, so let's say we've got a column. So this little diagram here in gray, we've got a column, it's got a particular length. The longest standing wave we could ever have fit in there, and we have to follow our rules, has to have an antinode at one end and an antinode at the other end. So the longest standing wave would be this shape. From here, swooping down to there, and down there, swooping up to up there. That would be the longest, that kind of sideways hourglass looking thing. Drawing it above so maybe you can see me draw it. That weird looking thing is actually a standing wave in air. So it's going to make sound. And that's the longest wavelength we could ever fit. The wavelength's so long that only that hourglass shape fits into the column. That hourglass shape is half a wavelength long. So half a wavelength is fitting in the length of the column. Since it's the longest one, that's the lowest frequency or lowest note that we could get out of that air column. We only have one kind of name for this. It's called the first resonance. We don't have to worry about harmonics or overtones. So the first resonance is the longest wave that'll fit in our column. It's going to correspond to the lowest frequency, and it would be half a wavelength fitting into the air column. If we take the exact same air column, but we kind of blow in it a little bit differently, we could jump and have another standing wave set up inside that air column. We have to follow our rule, so we go from an antinode, but instead of stopping at the next antinode, which would be kind of that original shape we saw, kind of here's our next antinode, we squish the wavelength shorter so that the next antinode is way over at the other end. So we get a standing wave. Here I'm going to switch colors this time. That kind of follows this, top to bottom to the next antinode. So here's an antinode to the next antinode still in the column to the next antinode at the end of the column. So we've got antinodes at the end of the columns and one in the middle. What we've done is we've squished the wavelength so that that standing wave pattern can fit in there. So it's a shorter wavelength. So this would play a higher note. It gets called the second resonance. And we've kind of got two of those hourglass shapes, or we started at a crest, went down to a trough, back to a crest. That's a full wavelength that's squished into there. So second resonance, we have one full lambda fitting in the length of the column. If we keep it going, if we were to jump and play the next standing wave, we would have to squish the wavelength down again, so a shorter wavelength. So if we start at it, we have to start with an antinode. Start at an antinode, next antinode is there, second antinode is there, third antinode is way over there. So our standing wave goes kind of like that shape. If we count it out, this is half a wavelength, this is another half a wavelength, this is another half a wavelength. So in the length of our air column, we've got 3 half wavelengths. We call that the third resonance. And again, it's a kind of shorter wavelength, so a higher note. All right, I know that's a little bit weird, but look at there's a connection here. The first resonance was 1/2 a wavelength in the L. The second resonance was 2/2, which is the same as 1 lambda in the L. The third resonance was 3/2 lambda inside the L. Really what that means, and if you've played the recorder, you know this. Let's say you set up your fingers and you're not going to change them. So you're covering a particular number of holes and you're not going to mess around with it. When you cover, let's say you're covering the first 3 holes, if you blow slowly, you're going to play a low note. That's kind of like that is your first resonance, that low note. And then if you blow harder, it's not going to slide up through a bunch of notes. It's just all of a sudden going to jump and play a higher note. What you've done is you've jumped from the first resonance to the second resonance when you blow harder like that. And if you blow even harder, you could possibly jump to the next resonance, an even higher note. You can't play any notes in between. You could play that low note as long as you keep the holes the same. So you're covering those first 3 holes, let's say. You could play a low note, then you blow harder, you're going to jump to the next resonance, the second resonance, to another note. And if you blow even harder, you might be able to jump to the third resonance, an even higher note. And before you can jump to the fourth, your siblings or parents are going to storm in the room and tell you to quit messing around with the recorder because that's annoying as heck. But that's the guts of how a recorder works. Once you set the length, you can jump from one resonance to another. If you change the number of fingers you've pushed, then you've changed the length. So you would change less dramatically. You just stretch out the wavelength a little bit by covering another hole. So you would change the note by a little bit. But if you don't change your fingers and just blow harder and harder and harder, you're going to jump from one resonant length to the next. There's an example here. Open at both ends and 90 centimeters long. So that tells you kind of the length of the column. Third resonance, in disguise, the third resonance tells you the shape of the standing wave. From the length and the shape of the standing wave, from those 2 things, there's enough there that you can figure out the wavelength. From temperature, you can figure out speed. Once we know speed and wavelength, then V equals F lambda, you can figure out the frequency. I'm going to pause this video here because it's getting kind of long. Try that question, and then I'll continue on, and you can learn about the closed at one end.